KNN, the algorithm that's simple yet powerful, and it might just be the key to transforming your projects. Say goodbye to confusion and hello to clarity. Welcome to day 11 of the 30 Days of Machine Learning series, where we make complex concepts ridiculously easy. If you're just joining, don't worry. You can click right here to access the full playlist and catch up on every step of the journey so far. And hey, make sure to hit that subscribe button so the next video in this series drives straight into your feed. You don't want to miss what's coming next. In this video, we're breaking down KNN, how it works, and why it's a must-know for any machine learning enthusiast. Stick around, and by the end, you'll be confident in using KNN to tackle real-world challenges. Let's jump in. Starting strong by importing Pandas, NumPy, Matplotlib, and Seaborn, the essential toolkit for data analysis, numerical computations, and stunning visualizations. Loading the diabetes dataset into a data frame and previewing the first few rows, checking the dataset's dimensions, gaining insights into its structure, and summarizing statistical details to better understand the data. Creating a pair plot to visualize relationships between features, colored by outcome, revealing patterns and potential separations in the data. Calculating the correlation matrix to understand feature relationships, and visualizing it with a cool, warm gradient to highlight strong correlations. Setting the theme to white grid for clean visuals, then plotting a box plot for age distribution using a set 3 color palette, highlighting age spread and potential outliers in the data. Creating a large figure for a clear view, then plotting histograms of all features to visualize distributions and detect any skewness or outliers in the dataset. Plotting a bar chart to visualize the distribution of diabetes outcomes, showing counts of positive and negative cases for clear comparison. Dropping the outcome column to isolate features, then previewing the first few rows to check the updated dataset. Extracting the outcome column as the target variable, then previewing the first few rows to confirm the target values. Splitting the data into training and testing sets, using 30% for testing, ensuring reproducibility with a fixed random state for consistent results in model evaluation. Standardizing the features using standard scalar to ensure each feature has a mean of 0 and a standard deviation of 1. We fit the scalar on the training data, then transform both the training and testing sets to ensure consistent scaling, improving model performance and accuracy in machine learning algorithms. Initializing the K-neighbors classifier with 5 neighbors, using Euclidean distance L2 norm for measuring distances between points. Training the model on the scaled training data, enabling it to learn the relationship between features and outcomes for predictions. Making predictions on the test set using the trained KNN model, then displaying the predicted outcomes for evaluation. Evaluating model accuracy by comparing predicted results with actual test values. Generating the confusion matrix to evaluate the model's performance by comparing predicted values against actual outcomes, showing true positives, true negatives, and false negatives for detailed analysis. Generating the classification report to assess model performance with metrics like precision, recall, and F1 score for both diabetes and normal outcomes, helping evaluate classification effectiveness. Testing different values for K in KNN from 1 to 39. Training the model, predicting outcomes, and calculating the error rate for each k. The error rates are stored to identify the optimal k value that minimizes misclassifications for better model performance. Plotting the error rate against different k values to visualize the impact of varying neighbors on model performance. The graph helps identify the optimal k value, where the error rate is minimized, improving classification accuracy and ensuring the best k for future predictions. Training the KNN model with 13 neighbors, using Euclidean distance for neighbor calculations. This configuration optimizes model performance by finding the balance between underfitting and overfitting for better predictions. Making predictions on the test set using the trained KNN model with 13 neighbors and displaying the predicted outcomes for evaluation. Evaluating model accuracy by comparing predicted outcomes with actual values. Creating a heat map for the confusion matrix to visually represent model performance, with annotations showing true, false positives and negatives for better understanding. Generating a classification report to display precision, recall, and F1 score for both diabetes and normal outcomes. Assessing model performance in detail. We've explored KNN, fine-tuned it, and evaluated its performance with metrics like accuracy and confusion matrix. But we're just getting started. In the next video, we'll dive into naive Bayes, another powerful algorithm that simplifies classification tasks. Click on the screen to continue and discover how naive Bayes can level up your machine learning skills.